good to see you all. So today's speaker is Andres. He's doing a PhD in Edinburgh University under Professor Arjun Berera, and he's working on chaos and turbulence connections. So Andres, please, you can just start the talk. Okay.
All right. Hello, everyone. Thanks for inviting. Well, you won't see my face because my camera is not currently working, but I will talk through my slides. So yeah, I will present the work we did with Daniel Clark, Daniel Brenner, Arjun Berera, and also Richard Ho, that I didn't write his name here. It is also a PhD. So this work, in this work, we measure, there's a way of measuring the transition between 3D and two-dimensional turbulence using chaotic properties. So I will start first introducing a brief outline of the talk. So first I will be talking about chaos and turbulence and introducing those concepts. Then I will talk about chaos in three-dimensional turbulence, which is very different from the two-dimensional that we'll talk later. And I will also talk about the techniques we use to measure the Lyapunov exponents. That is a quantity that we will look at during these works. And in the end, our more interesting work in this direction is the transition between the three-dimensional and two-dimensional turbulence that we did recently. So let's start. As we all must know, turbulence is chaotic. This means not that it's a random phenomenon, actually it's deterministic, but it's very sensitive to initial conditions. So the first chaotic system were explored by Lorentz in the 60s. He did a very simple model of atmospheric convection with just 3 dimensions, and varying the parameters, he found that for certain choice of parameters, the solutions of this system is very sensitive to initial conditions. So it's a deterministic system, but if we let it evolve with a small error in the initial conditions, the solutions will diverge quite rapidly, actually exponentially. And this system tends to a strange attractor, what is called a strange attractor. So it is bounded in the phase space, but solutions will move around that area. And after a late time, 2 random solutions chosen at random, and I mean, they will be like, what I want to say, sorry. If we start from very similar initial condition, when let the system evolve, these 2 solutions will be apparently random, and they will have no correlation between each other after some time. So we look at this kind of chaotic behavior in turbulence, but there are 2 ways of looking at this. First, we have the Lagrangian framework, and in this case, one can measure the particle trajectory and its sensitivity to initial conditions. And it's been observed that even in laminar flows, one can have, like for example, in shear flows, one can have Lagrangian chaos without the Allerian. In the Allerian sense, the fluid being chaotic. So the Allerian chaos is when we have the whole field, the velocity field, u of x and t, and we let the system evolve, and at some point we perturb that slightly, so we have 2 very similar initial conditions, and for infinitesimally close solutions, these 2 different solutions will exponentially diverge. This rate of exponential growth of the error is what we call the Lyapunov exponent, and this is how we measure how chaotic the system is. So the larger the Lyapunov exponent, the more chaotic the system is. And it's important to note here that the Lyapunov exponent has units of 1 over time, and this will be important later when we try to make some predictions out of it. So any question that you have, please feel free to interrupt. And for any reason, if something is not clear, or if something was not clear in the audio or something, just please feel free to interrupt. So one of the guys who made very important progress in this area of chaos and turbulence is Ruelle. he explained, actually he coined the term of strange attractor, and he made some important papers in the 70s and 80s about how the onset of turbulence works. But a less well-known paper in the 1979, he predicts that using just dimensional arguments, that the maximal Lyapunov exponent should be associated with the smallest timescales of the system, which in 3D turbulence is the Kolmogorov timescale that depends on the energy dissipation rate and the viscosity. And this implies that the Lyapunov exponent scales as the Reynolds numbers to the 0.5 using Kolmogorov theory. So that was an important prediction made by Ruelle in that paper that was lost then in the literature, but many years later it was recovered, and we actually measure that using the numerical simulations that we will show later. So also a comment that if we use multifractal intermittency, so the multifractal model shows that actually the scaling should be a little bit less than 1/2. I will explain why I comment this later. So in our research, what we try to do is to study the chaotic properties of turbulence. We started with a very simple isotropic homogeneous turbulence, incompressible. But then we moved on to MHD, two-dimensional turbulence, and we are intending to measure other systems as well. So what we want to see is how predictable is turbulence in general, and what is this Lyapunov exponent depending on which parameters for the system. And then it is okay to ask if it's useful to understand predictability of flows in general, and if is there any other use in general of Lyapunov exponents. So we will discuss about that later when we get our results. Let's start with the work that Richard did a few years ago. So this was the first work our group did in this direction. The idea was to simulate a Navier-Stokes equation using direct numerical simulations, using a random forcing, and using, our numerical technique is just using a cubic lattice of varying number of collocation points. We did up to 2048 cube collocation points, and we use a pseudospectral method, and with a two-third rule de-aliasing, in case someone's interested in that. And well, this is the first picture that I'm interested in communicating. This I will show now what is the main technique we use to measure the Lyapunov exponent. This is the first technique we use. So the first thing we do is just run a simulation, and we let the system evolve until it reaches a steady state. And at some point during the steady state, we add a very small perturbation. So we create a second field, which is very close to the first field initially, to the reference field. And we measure the difference between these two fields point by point. We integrate over time, and that's how we measure the error. This 1/4 factor is there, so at late times, when these two solutions become uncorrelated totally, this error will be the same as the total energy of either of these two fields that are statistically equivalent.
So just for Andreas, end is one question.
Yeah, sure.
So the difference between U1 and U2, are they a small wave number, or which wave number or which band of wave numbers are you separating U1 and U2?
Sorry, again?
So U1 and U2 are slightly different.
Yes. So
for what K? Which wave numbers?
So we are here, we are integrating overall wave numbers, but in our case, we usually use, we use different spectrum for the initial perturbation. We see that the later evolution is not very relevant to the initial, but at first we used to force only the large wave numbers, Then we did some tests. Just affecting the higher wave numbers, and after a very short transient, the system adopts like a typical form and grows like this. Now I will show this now. If it works, there's an animation showing that.
Okay.
But yeah, the initial perturbation. I think for this work we used the large scale, so the small wave numbers.
Okay.
Just a very small. So here it is on the right hand side. You will see the fraction, the error fraction to the energy, and we see that it's 10 to the minus 8 approximately, and then it grows until it saturates at the value of 1. And on the left hand side you'll see the evolution of the spectrum. So the red line is just the spectrum of the energy in the steady state. There's not a large inertial range. We don't see a large inertial range because this was done for relatively low Reynolds numbers, but the idea is the same. And then the blue line represents the error spectrum. So if this works, you'll see something I want to. Yeah, so as it grows, it adopts a typical form, and then first the energies of the higher wave numbers become decorrelated first, and as long as the system keeps its progress, larger and larger wave numbers become decorrelated. And what is important about this, I will just show this once again, because this is a very useful picture of what's, well, it doesn't work again, but anyway, let's see. So yeah, so this is in line with the same philosophy that people in weather prediction understands, that the larger the phenomena we want to describe, the larger times we can predict it. So obviously, if we want to describe cumulus convection or cloud formation or microscale turbulence, let's say here, we can predict it for very short times, and the solutions become decorrelated quite fast. So we can predict it for only minutes, hours. But as we grow and we want to predict larger phenomena, that is predictable in larger time scale. So our picture of simple turbulence, 3D isotropic and homogeneous incompressible turbulence, which is very different to what we have in the atmosphere, that's coupled to many other things, is compressible. We see that the same picture is represented, which is like a nice prototype to understand this kind of chaotic phenomena. So, and also another thing I want to remark is that the growth is exponentially at the beginning. In later times, it becomes linear when the larger energies are still predictable. The growth of error is slower. So that's, let's say, a good thing in terms of predictability. Let's move on. So this is the work that Richard did. So he tested Ruelle relation, measuring Lyapunov exponents and the Reynolds number for each simulation. And he found that the scaling is very close to what Ruelle predicted of the 0.5, and is actually over the 0.5, contrary to the multifractal predictions. So yeah, any questions so far? Everything okay? Everything okay? All right, I will move on. So now I want to present a different technique we use to measure the Lyapunov exponent. So we measure the finite time Lyapunov exponent using, instead of perturbing the system once during the run and see how the system evolves, we add successive perturbations to the system, and at each time we measure, in each time window, we measure the Lyapunov exponents. This allows us to get a better statistics of the Lyapunov exponent behavior, because it has some important variants that we need to detect, that if we just run it once, we won't see that statistics. So this is also an animation. So when we run this, we see that the error grows, but if we rescale the system and we add another perturbation now, it can grow faster or it can grow slower. And what we want to capture is this variation and have a good understanding of the statistics. So we use that method and we measure the mean and the variance, and we observe like this is a very advantageous method not only to get better statistics, but the statistics of these exponents is very robust, and I will explain later why. But basically, we can change a lot of things in the system, even having not so well resolved simulations, and these quantities stayed the same, contrary to other quantities in the systems like Reynolds numbers and that. So the only drawback of this is that the picture that we saw before, the spectrum growing and the correlating the higher weight numbers first, and then moving on to the larger scales later, is lost because we don't have any idea what happens to the system at later times, because we are constantly perturbing the system. Well, so as I mentioned before, this measure is very robust. We can vary the time window we use for these perturbations to just a very few time steps, and the measurements stay the same. But the more interesting one for me was that when we let the system evolve, so here we have the histograms of the Lyapunov exponents of the FTLEs, and here in blue we have the Reynolds number statistics, and we see that for a certain time in the simulation, there is just this T, well, this is not the turnover time scale, but it's just a few turnover time scales, like 10 or something like that. And we see that the Reynolds numbers still doesn't reach like a definite statistics, a definite distribution, whereas the Lyapunov exponent has a quasi-Gaussian distribution already. And then if we let the system evolve to 10 times that, then the Reynolds numbers show like a more defined statistics, and the Lyapunov exponent barely changed. And this is interesting because there is like we observe that there is a very clear relation between the Lyapunov exponent and the Reynolds number. So not only the mean, but also the variance have some relation with the Reynolds number. So we can estimate these quantities just by measuring the Lyapunov exponent much faster than measuring the Reynolds number fluctuations. So another work made by Daniel mainly was on two-dimensional turbulence. So then he explored how chaos behaved in two-dimensional turbulence. And as we know, phenomenology in 2 dimensions is quite different. So we have an inverse cascade of energy this time and a forward cascade of entropy. And since we don't have any more vortex stretching, the Kolmogorov timescale that we had in 3D has no longer a meaning, and the unique timescale that defines this forward cascade is the entropy dissipation rate. So the prediction here is that the Lyapunov exponents will somehow be related to this entropy dissipation rate timescale. Measurements show that actually it does scale there is a good agreement between the Lyapunov exponent and the entropy dissipation rate to the 1/3. But we observed that these results also had some dependence on the scaling wavelength and the forcing wavelength and the size of the box that we use. So it's not entirely universal, but we could observe some relation that is very good. And actually, also if we take into account the logarithmic corrections, we also see extra dependence. Here's just the Lyapunov exponent scale but this time scale, and we see that it grows slowly with Reynolds numbers. And we assume this is related to the logarithmic corrections of the two-dimensional that we need in two-dimensional turbulence to have like a constant cascade. All right. So now I think this is a more interesting work using chaos in turbulence. in this case, we wanted to study the transition between 3-dimensional and 2-dimensional turbulence. So we have these two types of turbulence are very different. So many works in the past have been looking at this transition in different ways. For instance, in the 70s, using closure models, they treat dimension as a parameter, and they vary that parameter to see how the transition occurs. But lately, some people used different approaches. In this case, we use a geometrical approach in which we have a cubic lattice, and we start to reduce one of the sides, until we get a 2-dimensional system. So it's just a geometrical way of suppressing one of the dimensions. Obviously, a more realistic way will be to use stratified and rotational flows. I think Alex Sakis gave this talk in a similar subject last week. So this is in the same direction. Actually, the first results observed using this kind of rectangular lattice in thin layer were done by Benavides and Alex Sakis a few years ago. But first, I want to introduce an important control parameter that we use for the simulations. There is this Q here. So the ratio L to H is not very important here. And the reason for this is very reasonable, because, for instance, we live in the atmosphere that is a thin layer as well. But if we are we are forcing at very small scales, we have no information that the atmosphere might be 2-dimensional or a thin layer. So we live in a 3-dimensional world. But as we explore larger and larger phenomena, we start to see the effects of this thin layer. So the important ratio will be the forcing length scale to the height here, height of the Q. So this is, I think, it's been observed, this is the important parameter to look at for the transitions. So what has been observed in the past is that we start from a 3-dimensional cube, and when we start to vary this parameter Q when we increase this parameter, we are closer to the 2-dimensional case. So at some point, an inverse cascade will show up. So we have a whole region where we have like a mixed phenomenology. So we have some properties of 2-dimensional and some properties of 3-dimensional turbulence. So particularly between this Q3D and the QTD, that are the two important transitions that this system suffers, we have a mixed, a cascade in 2 directions, a forward and an inverse cascade, typically of 2D. So, yes.
Excuse me, I have a question.
Sure.
What is Q? Can you remind me?
Yeah, sorry, we go back. So
Q is a ratio. Okay, nice.
The ratio of the forcing, forcing scale to the height of this cube. So this is the ratio we look at, and the important one. So as we increase Q, as we see, we increase the forcing scale, and we start to notice that this is a rectangle and not a 3-dimensional cube. So we start to notice the 2-dimensional properties. I don't know if that's clear.
Okay, yeah.
All right.
Thank you.
That's okay. No worries, please.
And the 3D energy is what?
Sorry?
Oh, the E3D, the energy 3D.
I will talk about that now. So now I was talking about the cascades, but now, So there is, So first of all, there is a second point that is Q2D that depends on Reynolds number, and at this point, the cascade, the inverse cascade will be the only one, and the forward cascade will just disappear. And this is why, So about the plot, exactly, we increase Q over RE of the Reynolds number, and as we increase this, we approach the 2-dimensional situation. So what we measure this in this ratio is the ratio of 3D energy to the total energy, because it is possible to decouple the two energies by just looking at the wave numbers, the ones that have 0 wave number in the vertical direction are considered to be the 2D modes, and the ones that have some variation in the vertical direction are the ones that are 3D So we have this three-dimensional energy ratio to the energy, and at the beginning we will have some fraction of it that is three-dimensional, and as we increase this control parameter Q, we start to see how this energy decreases smoothly until it just disappears, until the three-dimensional energy is zero. This is typically when Q over Reynolds number is 0.25 approximately. So this will be the point where the not only when the forward cascade disappears, but also the three-dimensional energy obviously disappears.
So you mean and this you mean 3D means along Z direction or along the anisotropy direction? Is that correct? E3D. What is E3D? Is ZZ, right? I mean, along Z direction.
Along Z direction, yeah.
Okay.
So yeah, I mean, yeah, it's all the modes that have KZ different to zero. And also, yeah, we can also decouple the ones that have like a vertical component of velocity, but
I see. So you're just keeping KZ non-zero, and that is E3D for you.
Yeah, E3D is that. So yeah, now we want to look at comparison because we previously studied two-dimensional turbulence, three-dimensional turbulence, and obviously we want to compare our results in the thin layer to those results. But this is somehow complicated because it's not clear which scales or which Reynolds numbers to use for this comparison. And also we want to compare this work with the previous literature. So the Reynolds number that is used in thin layer literature is this forcing scale to the 4/3, energy dissipation rate, and viscosity. But all these parameters we can fix a priori in the simulations. So we notice that it's a bit better for looking at the scalings to use this second Reynolds number, the forcing scale, which is which leaves some freedom to for the system to decide in this. So we measure the energy, and this is not something that we fixed in the parameters. So yeah, so I will just, this is like how do we say, this is just something to keep in mind for the comparisons that I will do later. So this is mainly the results we got. I think this is a nice summary of the results we got in this paper. So let's first look at the right-hand side plot. So in this case, we have the Lyapunov exponent compensated by the time scale. In this case, is the entropy dissipation rate. We chose that, and we see the scaling with Reynolds numbers. And we see that the red points are those who are below this control parameter being 0.25, the transition point we observed before between 3D and 2D. And all these red points that are like three-dimensional scale very differently for those above this value, and have a different scaling properties and also different values. And all the yellow points are points that are close to the transition. So we see that these points are everywhere, the yellow ones. Now I move to the left plot. And this was interesting for us because what we did, it was just use the Reynolds number, this scaling of the red points, to just make this line flat. And we plot, instead of plotting the Lyapunov exponent against the Reynolds number, we plot the Lyapunov exponent against this control parameter. And we see a very clear and sharp transition that separates the two-dimensional and three-dimensional case. And this is contrary to the smooth variation we looked before for the case of the energy. And actually, this was reminiscent for us reminiscent of a first-order phase transition. And we looked in literature that actually some work in the past, not related to turbulence, but to other phenomena, used the Lyapunov exponent as a measure of phase transition in critical phenomena. This case was a case of DNA, but it was used in the 80s, actually in the 90s, and this is the last work we found that explore this this kind of research. But yeah, here's a comparison of the two plots. So here we see the transition with the energy, and we see a smooth transition. Whereas in the Lyapunov exponent, we see a very sharp transition. And we started to think why this is the case. And I think the most convincing argument, at least for me, was that as we start from 3D, we will always have a forward cascade. And as we start suppressing one of the dimensions, we start to lose some three-dimensional energy because some of the triadic interactions are just cut out geometrically. But we still have a forward cascade. And as long as we have a forward cascade, we will have a dissipation related to the Kolmogorov timescale. And that will be dictating the chaos scaling, the Lyapunov exponent scaling. But when we are over that, when the forward cascade is over and we only have an inverse cascade, so the Kolmogorov timescale has no longer a meaning, and there's a sudden transition to the two-dimensional case, which we don't observe in the energy. So it's a matter of suppressing this geometrically the system. But yeah, so that's the reason why we think there's a sharp and not a soft transition like in the energy case. So because chaos is capturing this timescale very well, apparently. So we thought that in this case showed us that the Lyapunov exponent not only has a very robust measure, but also is very good to determine some properties of the system. And actually, in this case, it seems like much more precise than the energy, for instance. So another comment that is interesting is that when we looked at the fluctuations of the Lyapunov exponents in the way we measure, so we have successive perturbations, so we have a lot of Lyapunov exponent to measure, and we can look at the statistics. And these are two runs with similar Reynolds numbers, but the blue one is far from the transition point, and the black one is one line there was measurement close to the transition point. And obviously here I'm showing two cases, but this is seen for all the cases actually near to the transition point, that we have very large fluctuations, and this is typical of phase transition critical phenomena, which we don't want to see that this is exactly that situation, but is very reminiscent of that, which is interesting. And the obvious possible applications are related to predictability, which in numerical weather prediction, all these chaos scales sometimes are not very important because the scales at which these systems are run are very large, and the chaos that we see in turbulence are only timescale relevant at small scales and small timescales and small also spatial scales. But in these last years, numerical weather prediction are building models that are running on very, very high resolution, actually meters, not even kilometers. So we think that as we increase the resolution of these numerical weather predictions, this transition in predictability might occur. So I think it's good to have a prototype of this in just a very simple model of turbulence to see that this is possible. And obviously these transitions have been observed in stratified and rotational flows, varying, for instance, Rossby number. So I think a good direction in the future is to get more realistic situations in our simulations and see and study this transition in more detail. So yes, these are the final comments. That in 3D we have Lyapunov scaling that goes with Reynolds number, as we well stated, Reynolds number to the 1/2. In two-dimensional turbulence, we have a good agreement between the Lyapunov exponent scaling as the entropy dissipation rate to the 1/3. But in thin layer turbulence, we have a sharp transition between these two situations. And this value have been observed also in other works. So we think the Lyapunov exponent is a very good measure of this transition. The question is whether this will be observed in geophysical flows. And in general, if the Lyapunov exponent is also a good measure of the transition in other types of flow. Last thing I want to comment is other of the research we're carrying out. We are doing now the same idea of changing dimension, but instead of moving to from between 3D and 2D, we are running DNS in 4, 5, and 6 dimensions, and we are observing that the system becomes less chaotic as we increase dimension. If we actually use EDQNM, like we played around with EDQNM simulations using the dimension as a non-integer parameters, and we observed that at some point, like around 5.8, the system becomes non-chaotic at all. So the Navier-Stokes equations become non-chaotic. I wouldn't say Navier-Stokes equations because obviously EDQNM is just an approximation that there's a lot of modeling there. But it was interesting to see that our EDQNM simulations show the same trend that we are observing here. But what we are also doing is try to find similarities we grab some of these forecast data of high resolution, and we try to see if we see some similarities in the way these ensembles evolve. If we observe some similarity to the things we observe in turbulence, and if there is any relation between two other parameters of the flow, like we have, for instance, between the Lyapunov exponent and the Reynolds number. And also we study chaos for passive scalars now, and we intend to establish a relation between Allerian and Lagrangian chaos as well. Maybe passive scalar is a good way to achieve this relation. And last, we are interested in applying this modeling to our DNS, stratification and rotation mainly, to be able to study this transition in more realistic scenarios. Well, that's all for today. Please, if you have any question, ask, and thank you for listening.
Thanks, Andres. Excellent talk. Okay, so we are open for questions. Okay.
I have a question.
Yes, Alexander, please.
Yes. Thank you for your speak. It's good. Okay, I have a question. It's about your DNS. Just
Yes.
Did you fix AH and you increase or you decrease the LF, the length of your forcing?
Yeah, we did both. We changed, so we use the length that is 2 pi over the length is 2 pi. So we have integer weight numbers. So we have like our forcing scale was always intermediate. I think it was 4, 8, and 16, and the height we vary more the height actually than the LF, but we vary both actually. Yeah.
But your box is very flat, no?
It's yeah, I mean, the interesting cases were when the box was becoming flat. So the ratio L to H was always rather L to H was rather high in general.
Okay.
But even for very small scaling forcing, we have 3-dimensional behavior when the forcing scale is.
And for both case, for 2D or 3D case, your Lyapunov exponent depend only on the dissipation scale.
Yeah, usually because these are the smallest time scales, and chaos apparently always is dictated by the smallest time scales. Obviously, the Lyapunov exponents, not only one is a spectrum. If we perturb the system at random, we will find that at some time the maximal Lyapunov exponent will take over. But Daniel did also study that I didn't mention here, in which he studied the Lyapunov spectrum instead of just the maximal Lyapunov exponent. And in this case, he was removing the modes that grow fast, and he started to show that at some point, if you start to remove those modes, you actually get to see the negative Lyapunov exponents. But yeah, if you perturb the system at random, after a certain time, the system will evolve as the maximal Lyapunov exponent dictates.
Okay, and just for the clarification, you have one field for one time, and after you introduce some perturbation, it's a random noise. You add some random noise onto your field.
In which case, in the FTLEs you mean, or in the or in general?
Both in general, yes.
Yeah, because the techniques used was different. In this case, what we do is we let the system evolve, yeah, and then we measure the difference at this when this time ends, when this first time window ends, we measure the difference between the two fields, and we just multiply by a factor that brings the error down back to this point, and we run it from there. So the perturbation that we add is based on the evolution of the fields of the previous field at the final time. So we rescale the error using the previous error.
Okay, thank you.
All right.
Okay, so Selend, please go ahead.
I am here. That's a nice talk.
Thank you.
Thanks for presenting these results in such a nice way. Can you, probably I missed it, can you please explain why there is a sudden jump in Lyapunov exponent from when we go from 3-dimension to 2-dimension?
So I wonder, question is on this, oh, sorry, this plot, right?
Yeah.
Yeah. So yeah, as I was mentioning before, we suspect that the reason for this is that when, as I mentioned before, we start from a 3-dimensional case, so we have a typical scaling of 3 dimensions, and we start to increase, and the typical physics of 3 dimensions. When we start to increase Q, we start to see the appearance of an inverse cascade. But since chaos is related to the smallest time scales of the system, this is so the smallest time scale of the system is where the forward cascade is dissipated. So as long as we have that forward cascade, we will have the chaos being dictated by the 3D time scale. Even if we have an inverse cascade and many things going on in the larger scales. As we start to increase Q and Q more, we start to lose 3-dimensional energy, but we still have this forward cascade and the Kolmogorov scale dissipating energy. And as I said, the system will find its way to the maximal Lyapunov exponent. So we still will see, and until the last moment, we will see this 3-dimensional physics. Only when the forward cascade disappears and energy is no longer being dissipated at the Kolmogorov microscale, only there we will see this jump to the physics of the so whereas the energy transitions smoothly, we see that chaos transitions like sharply. I don't know if that's clear, because energy is taking into account all the physics, what's going on in the cascade, the inverse cascade, the larger scales, the middle scales, higher scales. Whereas chaos apparently is only detecting what's going on with the smaller time scales.
And this figure also suggests that the inverse of Lyapunov exponent, which in one of the previous slides you have said that it is predictability time. So this also suggests that predictability time has increased suddenly, right?
Yeah, that's somehow something that surprised us, at least in the region we are looking at, because we look at the previous plot, we see that at some point for higher Reynolds numbers, there might be actually a crossover. And for the scaling we use here, we should see a straight line in the red lines, but the blue lines should start to decrease at some point because of the scaling we used. And here, I mean, we don't see that because there's a lot of variance here. Even though we see a sharp transition, it doesn't mean that we will have like a constant situation if we keep increasing this value. But at least in this region we analyze here, we see like a jump between these two cases. But yeah, it was surprising for us that we suspect that 2-dimensional energy will be more predictable, and in this region the contrary is shown. But yeah, something I wouldn't understand too much for now. I don't have a quick answer that why this happens.
And finally, this 2D turbulence, if we like mimic it with the atmospheric turbulence, so does this predictability like can be attributed to the PSD predictability of the atmospheric turbulence? Can it represent that? Can it be a good measure of atmospheric predictability?
Sorry, can you talk louder, because I hear a lot of noise and I don't hear very well.
So can this predictability for 2D turbulence is a good measure if we consider the atmospheric turbulence?
Well, actually, as I said before, when the only way it's very hard to study when we talk about predictability in the atmosphere. There are many factors included. Not only there is a much more complex physical system, but one thing is to compare the prediction of a model to the observation. And what we do is slightly different because it's running like two simulations with similar initial conditions and compare the model with the model itself. So it's a property of the model. So the closer thing we can have to observing some of this in the case of predictability in the atmosphere is to see how many meteorological centers use ensemble prediction, that is doing exactly this, starting with an initial condition and then running like 10, 12 or 18 simulations with similar initial conditions and try to see if this covers the whole probability space of what's going on. So only in the last years, I would say that we're getting to a time and spatial scale that we are able to see this. But as far as I know, we are still two-dimensional turbulence is still very far of what chaotic turbulence is, because there are many other factors that make the atmosphere actually more predictable than what 2D turbulence shows. Yeah.
Okay. So we go to the next question, Rodion.
Oh, yes. Thank you very much for your presentation. So I have two questions. Do you hear me?
Yeah, sure.
Yes, yeah. Two questions. First one is fundamental. Sorry if I miss your comment on that in introduction.
No worries.
But as far as I know, the classical way how to define Lyapunov exponents is to measure the difference between two trajectories distance. So initially, if they are close, then we measure the distance between two trajectories, but not between difference between two flows.
So yeah, so I think I was discussing.
So, my questions. Question. Obviously, this is different techniques. I mean, technically, this is different because in this case, I can easily write down equation for delta ut, because this will be linear equation versus this delta until it is small, of course, but which is not the case if I follow some trajectories. So can you comment, will I obtain the same lambda if I will follow your techniques or classical one?
So let me see if I understand. When you mean classical, it's just grabbing one solution.
Classical, you take the flow. Sorry?
I guess you are asking he's computing using energy, which is the total of many directions, or it's not your exponent lambda is computed by energy, which is not the phase space, right, Rodion? That's what you're saying?
No. Classical definition, again, maybe it is too old school, but you imagine you have a flow, and it is evolved. It is just one realization of the flow, and then you take two particles. Imagine you take two particles which are very close each other from the beginning, and then after some time they diverge, and you measure the distance between these two particles.
No,
Yes.
Rodion,
No
that's not that. Chaos, you measure the separation in the phase space.
Okay, so then I'm wrong. Sorry, if it is wrong, I will check later with the book. Sorry, if
so
it is
phase space, but phase space. In fact, Andres is not doing the phase space. He's doing some kind of average over the phase space by computing the energy. You get my point? Like Lorentz equation has 3-dimensional phase space. If you have n particles, then it is 2n-dimensional phase space, and there is a difference in the trajectories in that space. Rudian, you get it?
No, I'm sorry. I don't understand why you are speaking about phase space. I'm just.
Chaos is defined from the phase space. Chaos.
No, not phase space. No, it's in physical space. In real physical space, I follow two trajectories.
Let the speaker answer. I don't
but is it true? So maybe just say, is it true that I can just write down equation for delta ut for this one, the delta?
So yeah, what I confuse about your question is if you are talking about particles. You are talking when you say particle, or you're talking about the fields, the state of the flow, of the whole flow.
Okay, then I will look this.
No, that's okay. I just wanted to understand your question, but because I think if you write the equation, you grab a field. Let's say you grab a field u of xt, and you add a small perturbation, and you want to write the equation for that perturbation. You will see that the non-linearities, even you will see that.
I think Andres, let me rephrase the question.
Yes.
Just for there are several ways to see the divergence.
Yes.
In Lorentz equation, the divergence is, in fact, there are 3 exponents, 3 Lyapunov exponents, right?
Yes.
Okay, because the space is 3-dimensional. Okay?
Yes.
Of course, in your experiment, it is a very large dimension.
Yes.
So it is hard to, in fact, it's 2n dimensions, right? For 3D, 2 orthogonal dimensions, right? For every wave number, there are 2 of them, Cray-Haring, right?
Yeah.
So you can't do it visually. That is impossible. So I think you are doing by using energy, which is integral of the mod delta u squared.
Yeah.
That is more like an approximation you are making for practical reasons.
I'm sorry, guys. I just meanwhile I just look in Wikipedia what is the Lyapunov exponents, and this is exactly what I taught my students. This is distance between 2 trajectories. But let's skip it, okay? Because this is maybe too general question. So may I ask you about your results, where you explain the effect of two-dimensional flow, especially about inverse cascade. So each time I hear about inverse cascade, I prefer to see some proofs that indeed you have this inverse cascade. And do you have spectral fluxes in order to confirm that indeed you have a negative spectral flux?
Yeah, not only we measured this, we didn't show in the paper because this was also observed. But we did in our test runs. We observed this inverse cascade, and this is shown in Benavides and Alexakis 2017. They actually studied with a different code, but the same idea of just making one of the dimensions smaller, and they show the flux of inverse cascade actually appearing.
Okay. Since you cannot show it, but can you say, is it indeed you observe some range of scale where the flux is constant and negative, or it is not constant and negative in the certain range of scales?
Yeah, between if we run steadily, if we run steadily, yeah, we use a different dissipation for the large scales. But once that is reaches steady state, yeah, it's a constant flux. We use hypoviscosity to dissipate the energy built up in the large scales. But yeah,
because it is really hard to find a numerical simulation with such a pronounced inverse cascade. What I mean that in certain range of scale, say 1 order of magnitude, we observe the constant negative flux from smaller scale to larger scale. It is very rare simulation. But thank you very much. I will look these references. Thank you.
All right, sure.
Okay. So next question, Raja.
Yeah. Hi, Andreas. Is excellent talk and very insightful.
Thank you very much.
I just have two very quick questions because I'm not here from field. So I'm just curious to understand page 27 regarding the Lyapunov exponent, not in terms of transition. Is it possible for, 27?
Yeah, 27. Yeah.
Correct. How to understand this Lyapunov exponent bit smaller in 3D to a bit higher in 2D? I mean, how to physically sense such low values in the case of 3D to such bigger values, an order of magnitude higher in perhaps 2D?
I think that's actually a very good question, and I don't have a clear answer for that. Actually, that's what if we go further, we are exploring that. Even if we go to higher dimension, even the change between 3, 4, and 5 dimensional is not so abrupt as the 1 to 2 dimensional. But in 2 dimensional turbulence, we know that there's a buildup of larger eddies, and one expect that system to be actually more predictable, and we observe the contrary. So the first I have to say is that, yeah, I mean, I don't have a clear answer for that. We thought about that. And as I mentioned before, because someone asked something similar, this is what we observe in this scale. Maybe when we go to higher realms, we observe a crossover. But anyway, I don't have a clear answer for that. Actually, it surprised us, but we didn't come up with any convincing argument for this.
I see. And the second question is,
well, if I can just step in, I mean, this is something that Andres mentioned. We're looking at higher D. I mean, this is something that we are looking at further. Yeah, we don't have a physical answer, but we are trying to understand its behavior because it is quite fascinating. So you know, if anybody has any theoretical ideas or anything like that, you know, feel free to you know, explore that, because there is something physical here, but we haven't been able to pinpoint it.
Okay, shall I make a comment, Arjun?
Yeah, sure.
In StatMech, we know that 2D and 1D have no phase transitions or no ordered states, right? And 3D has possible ordered states. So of course that is equilibrium statistical physics, but maybe 2D does show some more randomness, more disorder.
Yeah,
that may be showing up in the Lyapunov.
Yeah, exactly. And in fact, this is the reasoning in which I started looking at 4D, was the whole Wilson-Fisher fixed point in 4D and how, you know, you lose fluctuations. So there might be some analogy between what's going on in StatMech to what goes on in turbulence, and that's what one of the ideas that we're trying to pursue. But you know, we don't know for sure. That's all I can say. Of
course. I mean, they are two different.
But I think it's a fascinating behavior, and you know, if anybody has even developing the statistical mechanics idea further, you know, is open territory right now to look at. It's in fact very fundamental.
Something on Euler flow. I'll send you one paper which we are writing it. I'll send you that.
Yeah. Well, you can write it and then send me.
I'm finishing it, so once I finish it, I'll send it to you.
Yeah, but I think there's a fundamental point here that is worthy of exploration. So
of course. And
that's what we're looking at too.
Indeed. Great. Okay, so second question.
Sorry, Andres, go ahead.
Yeah. And second question, like the energy forcing, whatever we do for 2D and 3D, in terms of maybe per unit area or per unit volume, are we forcing in the same way? I mean, I'm just asking stupid question, but I'm just wondering, like the energy density, what we pump in, both the systems more or less same, and still do we see such kind of an order of magnitude difference? And can the supplementary question to that is, in case if I'm forcing similar energy density in both the systems, what it means, like having this Lyapunov exponent quite high in 2D, that means maybe either the particle pair dispersion is quite different, or perhaps the velocity decorrelation is quite in 2D. That means where exactly that energy really get destroyed or transported compared to 3D. I mean, like it's not in a position to dissipate energy in 2D to a greater extent compared to the 3D. Is that the way I should interpret, or is it something different? Am I making sense at all?
Sorry, yeah, I'm a bit lost with the question. So you're meaning that if there is
I mean, can I feel like these particles are perhaps the velocity decorrelation is quite high in 2D compared
Raja,
to
they're
3D?
not particles, they're particles.
Correct. Maybe velocity decorrelation.
That's okay. Yeah, no worries.
Okay.
Is that quite high in the case of 2D compared to 3D? That means, can I say that 2D turbulence is a way quick in some sense of dissipating energy compared to 3D?
It's very quick.
Yeah.
It's very quick. I mean, what's your question in terms of the energy? Because I mean,
if they are decorrelating very far distances or far time scales during their travel or perhaps motion, in some sense, do they dissipate energy as they travel because they are going for very far distances, or maybe in terms of velocity correlation, if I'm talking?
Raja, I think let's probably, you can send an email. I think the question is also not clear to him.
I see.
Probably
no worries. Yeah, I didn't understand.
So maybe just send the. I think
sure, sir.
To me also is not clear. So maybe formulate it and talk over privately.
Fine.
He's not
That's
talking
okay.
about particles, I think. Okay, so we'll just keep it already half an hour for question.
Correct.
Yeah, just
Thank you so much. So nice of you.
Yeah.
No, please.
Yeah.
Thank you.
Okay, so I think maybe I'll ask one last question before we quit. Actually, the initial condition is not quite clear to me. Suppose I want to simulate and test it out. So you can go to the previous slide, which I asked the first question, no? Where you had this movie where things were, the movie will make it clear. Maybe you can unshare it and then share that stuff. So the movie, you can play it again. And that, so when you choose here, looks like the difference is, yeah. So actually here, the delta U. So you had the velocity field, all the components.
Yes.
Then what is the new U prime or U1, U2? All looks like you are everywhere. I mean, the changes are, I didn't quite understand what is your new field, U1 and U2.
UN and U2. So this, what we do after the Allerian perturbation is to evolve both fields independently using a Navier-Stokes equation. But the first, you're asking about the initial spectrum.
So I thought you have already evolved it. Let's keep that, make it U1. Then U2, yes. You should make a small change, right? I mean,
yes.
You want to make a small change. But
yes.
Where are you changing? Like in Lorentz equation, we have X, Y, Z. So three components, and
yes.
you can change. But here, you don't want to change everywhere. No, I mean, maybe you want to change some wave numbers by some small amount. So you have that detail with you, or?
Yeah, I mean, what we do is like instead of using, because we do the perturbation in the spectral space. No, we don't do it in the XYZ simulation. So, as I say, in this case, when you start the 3D turbulence, what we did is to just add like I think it was a, let me think, it was a random noise, but just for the lower wave numbers, so only 1 and 2.
Okay, I will look at the paper and more carefully.
Yeah, but I don't think that's not clarified in the paper actually. But yeah, that's what we did.
Maybe you can send me an email. I just wanted to know this precisely. Which wave numbers are you disturbing, and by how much?
I'm sure this is a small, very small. Yeah, I mean, how much is in this? Like when we average it all, it's just 10 to the -8. And this is only certainly The only difference is in the larger wave numbers for this simulation. But as I said before, we tested that changing. So in another simulation, I perturbed only the higher wave numbers.
Okay.
And what I observed is like in a very, very fast transient, we get this growth that I showed in this animation. So this initial growth is adopted like instantly, almost instantly after the first few time steps, regardless of the wave number that I perturbed. So yeah, just that.
I see. Okay.
It was not very important.
And what if you change the perturbation or delta U at the large wave, small wave numbers, large scales? Did you try that?
Yeah, that's what I mean. I mean, we end up with this spectrum, this error spectrum, accommodating really fast to this typical spectrum of the growth that I showed in the animation.
I see.
No matter which. Yeah, this is the spectrum that we will observe regardless of the wave number we perturb.
Okay, and just send me this difference. How do you do it in email? That will be.
Yeah,
nice.
sure.
Okay.
Sure.
All right, so I think we'll end now. I guess there's no more question, and thanks a lot for being patient and answering all the questions. And
no, please.
Yeah. Okay. Great. So next
Thank
week.
you very much for inviting.
Oh, my pleasure, and thanks for accepting our invitation.